For that, we have to know what is a neural network. So, what is a neural network? Okay, for that, you have to know where neural network came from actually. So, actually, it came from neurons. Neurons are fundamental units in your brain which are responsible to communicate and transfer information. Okay, so it's a neuron is like a cell. It's like a cell. Where many of you in your biology classes must have seen that neuron has a structure. It has axons. It has axons, and it has this. It has this nice looking structure, and these are the dendrites, which are responsible to connect with another neuron. Connect for another neuron. Okay. Think it is as a neuron. Okay. Fine. So a biological neuron is a unit cell in our nervous systems. So, and actually, do we have a single neuron in our brain cell? No, we have millions of neuron cells interconnected. What topology they are interconnected, we don't know. Research is still going on. Okay. So, a network of biological neurons forms a complex neural network. Okay. And similarly, a network of artificial neurons, with a proper activation function is referred to as artificial neural. So how this connection is being made? You have millions of neurons in your brain, millions of neurons in your brain, and these neurons are connected in a complex topology, in a complex topology. And due to this topology itself, if someone pinches you, you will know within within less than a fraction of a second, you will know someone is pinching you. So therefore, this is responsible to transmit information very fast. Till now, research is still going on to understand what is the network of neurons, what is the topology of the neurons to understand and process information. Okay. This is what many of the students were doing this work with me. Like, what kind of topology you need to consider? Like schizophrenia and your other, like, can you tell any other name of that? Epilepsy that you get the feet again and again randomly. So all these behaviors happen not only due to the poor cells, but also due to the topology in which neuron is connected. So the topology of neuron it get connected is responsible. Okay, maybe your neurons are like this, are connected like this, and there is a hub. Okay, they are transmitting information to these hubs. This is known as a ring and a star. This is the star configuration. And also you have this info like this, and you have this ring kind of structure. And ring and star can be joined together. This is kind of ring star network. This kind of thing you might have seen in Interstellar. This kind of thing might have seen in Interstellar, and can give you, and also seen in cyber security areas, cyber threats and all this. You want to transmit information. So my work usually revolves around this area. Like, we want to understand what kind of spatiotemporal patterns you are seeing in these neurons, okay, and whether it is able to transmit information in a well manner. Okay, so therefore, sometimes in brain you don't want synchronization. Like, when you clap all together, you don't really know each other. You don't really know. Mintu doesn't really know when Durga is going to clap. So far. So you don't really know, but still you clap together. That is known as synchronization. Yes. So therefore, when someone claps in a wide, big audience hall, everyone claps together at the same. So that's synchronization. But in brain, you don't need synchronization. Brain, you need chaos. And if it is chaos in the brain, it works in a proper way. Brain should not be in sync. All neurons, if they are in sync, you will be prompted to do the same thing again and again. So if brain is in chaos, that is in a very unpredictable and very unsynced way, it is able to do proper tasks. Activation of topology in neurons, but by motivated from this, we consider a network of. So now you know millions of neurons are able to do complex tasks, complex information processing. Okay. So in a similar way, artificial, what we do, we see how nature evolves. We see how nature evolves, and we try to mimic that. We try to mimic that thing computationally. So the same way, we try to mimic this millions of interconnected complex topology of neurons in case of computation. We try to implement it. How we can implement it? Consider artificial neurons. Instead of biological neurons, you consider artificial neurons. Consider artificial neurons together with selected activation functions, See what is this activation function, what is its role. But together, this is known as something, a neural network. But since this is constructed artificially, it is known as artificial neural network. Okay, or ANN. Okay, so I hope that is clear how we actually landed to ANN. Okay. And actually, researchers then found that ANN can also do complex tasks, complex information processing. So therefore, it got very popular. So that's the idea so far. So an individual neuron, biological or artificial, can perform simple tasks, but when they are combined, when they form a network, they can actually perform very complicated tasks. Therefore, we don't need to study artificial neuron, but we are studying artificial neural network, because network as a whole can consider or process a lot of information apart from just an single artificial neuron. So come across, okay, this is where we come across. Like suppose you want to do multiple linear regression or simple case linear regression. We'll see. Maybe first we should see linear regression first. Yeah. Then we'll come to multiple linear regression. You can see that after you learn this linear regression from the point of neural networks, you can just generalize it to multiple linear regression. Okay. Fine. So what we already know regression is a part of supervised learning. Okay, supervised learning. Okay. Then suppose in simple linear regression, simple linear regression, what we have a training data set. We have a training data set. That is, suppose T is a training data set. What data you will have? Xi, Yi's. As usual in regression, I equal to 1 to n. You have Xi's and Yi's. What you want to do? You want to construct a regression line. You want to construct a regression line that can approximate the data set and can predict what should be the next value of data set at a given value of a independent variable. Okay. So training data set in machine learning jargon, I already told. What is this called? X's, inputs. Yes, features. And what are YAs? Labels. X's are features, YAs are labels in machine learning terms. In regression terms, in numerical method terms, you will say X's are independent variables, YAs are dependent variables. Okay. I hope this is clear. It is just a terminology we are working. This is the terminology. Okay, fine. What is our aim? What is our aim through this? Our aim is to predict what is the value at some x star. At a given x star, what is the value of the data set? What is the value of the data set? Okay, this y star, some y star. Fine. So our job is to do a simple linear regression. So our job is to fit a linear model, that is y cap equal to w naught plus w1x, fit this curve regression line to the training data. This to the training data. All right. Fit this to the training data. So the idea is simple. You have the training data set that is xi yi I equal to 1 to n, that you fit into the regression model. What is the model? Y cap equal to w naught plus w1x, and the output will be w naught and w. Fine. That's the logic. So after w naught, w1 are evaluated, we can estimate what is y cap at different independent variables, and that's the regression. But geometrically, how can we think of this? Geometrically, y cap, how we can think y cap equal to w naught plus w1x geometrically? How? This is the most important thing, and I want you to use your mind a bit, use your brain a bit, so that this serves as a purpose in your multiple linear regression also. And this will be the framework for multi-layer perceptron also. How we can think of y cap equal to w naught plus w1x geometrically? Geometrically in the sense through a neural network perspective. You must have learned about neural networks. So can you implement y cap equal to w naught plus w1x using simplest neural network? Any ideas? Yes, exactly. So you have already learned it. So pass the inputs 1 and say x to the weights, that is w naught, w1. Okay. So you can see w naught is known as a bias because it is acting on a constant. What is w naught? W1. So 1 gets multiplied with w naught, x gets multiplied with w1, and there is a summation that needs to happen, w naught plus w1x. That summation needs to be carried out by this summation operation. Okay. Then this is w naught plus w1x. Okay. But then this is z, suppose, and this will go through the activation function some phi. Okay, some activation function, and then it will be the output, that is, yes, y hat, that is w naught plus w1x. So can you tell me, here z is already w naught plus w1x. So what is this phi doing here? What can phi be? So that this z is again z here. Yeah, that's true. That's true for general neural network. But here we are talking about the regression. Yeah, one or identity. If you apply phi of z is nothing but z. Phi of z is nothing but z. Then if it takes z, it will also output z only. So therefore, y cap equal to w naught plus w1x. So just carefully remind yourself that in regression, your activation function is the identity function here. For classification, how this changes? For classification, what kind of activation function you will take? Can you answer? For classif, suppose you have two apple and oranges. Okay. So we simply need to do binary classification. Yeah, any step function can also work. Binary, we'll see that. So that's the idea. Okay. So this structure resembles that of an artificial neuron. This is how artificial neuron looks like. So this is an example of an artificial neuron. Okay, this is how a single artificial neuron functions. Okay, fine. So I think that's good. Now let us come to multilinear regression. So this is simple linear regression. Let us come to multiple linear regression. So multiple linear regression, what it does? So again, it is a form of supervised machine learning. So you have this data set again, xi, yi's, I equal to 1 to n. Okay. Feature and labels. Similarly, we have to predict what is y star at given value of x equal to x. Okay. Fine. So suppose in multiple linear regression, you rather have now this. Instead of w0 plus w1x, you will have multiple inputs. That is w0 plus w1x1 plus w2x2 plus so on till wn(xn). Now how you can classify, how you can construct a neural network for this one? Anyone? Can you draw in your notebooks? Let us check. Can you draw an artificial neural network for this multiple linear regression? I think it is easier. It's not that difficult. What you have to do? What we have to do? Any ideas? So we can give this 1, x1, x2, so on as xn as inputs to w0, w1, w2, so on, wn. Yes, and those are summed. Summation. Then again you get this activation function. So this summation you get z, that is this y cap. Okay. What is this phi does? It is simply a linear function. Okay, simply a linear function. What it does, it gives us y cap, that is w0 plus w1 x1 so on till wn xn. Okay, this phi is the activation function, and in regression this is just a linear. Okay, so this is a multiple linear regression, how it looks like. Fine. Okay, fine. Now let us come to the classification problem. Okay, the classification problem. So how can classification be carried out using this neural network? Again, classification, you already know it is a supervised machine learning. Okay, fine. So in classification, also we get a training data set, that is some xi's and yi's. Based on that, we need to classify them. We need to classify these n entities into different data sets, into two different or three different or multiple classification. Okay. So the label y is categorical. The label y will be a categorical variable. Categorical variable. Whether it is an apple, whether it is an orange. Okay. Fine. Or good or bad, pass or fail, those kind of categorical variables you can have. Fine. So you can interpret those categorical variables into 0 or 1, like a transformation. Okay. Fine. So if you want to segregate your data set into two classes, classify into two classes, it is known as a binary classification. So classify into two classes, binary classification. It is known as binary classification. If you want to classify more than two classes, it is known as multi-class classification. Okay. So we'll see how it is done. So same here also you have the same neural network structure, that is 1, x1, x2, so on till xn, and corresponding to each there will be a weight w0, w1, w2, so on till Wn. All these are summed, summation, and then you generate the result. Okay, but now you have this activation function phi. Okay, this is the activation function, but this z is that just y cap equal to w0 plus w1x so on till wnxn. But after that, how you will carry out the classification? You will say if z is greater than 0, then put 1. If z is else, put 0. Like that you can classify. So you can see phi of z is an activation function given by 1 if z greater than 0, 0 else. So using this, if you classify, you get the classified data, that is yk. So can you see the difference between regression and classification? Regression and classification both is similar kind of neural network, but the activation function is different. In regression also, you saw the same neural network in regression, and also for classification, same neural network. But the activation function is different. For classification, the function is like a step function, whereas for regression, the activation function is the identity function. Okay. So you might expect a question like, for draw the neural network for simple linear regression and draw the neural network for multiple linear regression. Okay. And how the activation function in regression differs from that of the classification. Kind of question you might expect. Okay. Fine. So you can see like what are the weights? What are the weights? The weights are those entities which tells you whether a particular input is important or not. So if your particular W2 weight has increased, then you are saying that you give more importance to the input X2. If W0 or W1 is low, you are saying that you give less importance to the input X1. Okay, that's the importance of that weight. So as I told you, regression and classification problems lead to similar artificial neurons, but different activation function. I hope that is clear. Okay. Yeah. What we have done so far? What we have done so far? So depending on your problem or project, you can have different activation functions at your place. You can have this sigmoid, many people were telling. You can use tanh, you can use relu, any other things. Softmax function and all. But we saw in class during optimization why we usually consider relu and not tanh in most of the problems. Okay. I think these are all good. So you already know all these things. So yeah, if you usually use perceptron for classification, perceptron is another particular kind of artificial neuron, so which you use for classification problems. Okay, we'll not go into deep into that, but there are learning rules for perceptron and all. But I think yeah. So the idea is simple. Okay, let us do for classification because it carries an important concept. Okay, you can take the notes if you want to know more, but we'll do for classification. Okay. So perceptron actually, as you already know, it's the simplest artificial neuron which can carry out classification. And perceptron learning rule, basically an optimization algorithm. So it's an optimization algorithm. It's an optimization algorithm that finds appropriate appropriate weights to minimize the difference between the actual and the desired outputs for the training data set. Okay, fine. That minimizes the training error, you can say. That minimizes the training error. That minimizes training error. Okay, fine. So Consider a perceptron with one input, that is x0 and x1. So suppose your input are x0 and x1 vectors, say the transpose. Okay. And you are considering that activation function. Since it is classification, you can use the activation function like 1 if z is greater than 0, 0 else. This is the activation function, this is the input. So how can you see it? 1 is given here, x1 is given here. Yeah, suppose x0 is 1, suppose x0 is 1, suppose. Then what you do, these are the weights. These are the weights w0, w1. You carry out the summation operation that will give you the z vector. Then you give this to the activation function phi to give the output y cap. Okay. Phi is given to you here. Okay. Now what is the perceptron output? Perceptron output is y hat equal to phi of z. Phi of z. Now what is z? What is z? w0 plus w1 x1 plus so on till wn xn. But this is very hard to write. Long operation. Can we write in some summation form? How? Can we write it in a vector form? Yes, you can write it as w transpose x. You can write as w transpose x. X is a vector, w is also a vector. W transpose is a vector of weights, and x is a vector of input variables. Okay. If you take the transpose, w transpose and x, you are actually multiplying w0 with x, x0, w1 with x1, wn with xn. That's how you get the summation. Okay. So this perceptron solves two classification problems, two class classification. That is, if there are two classes, perceptron can be used. Okay. Fine. Suppose you want to classify the problem, the data set X. What is our aim actually? Aim is to classify the data X into two subsets C1 and C2. That is two classes C1 and C2. That's the idea, right? That's the idea. Apple and oranges is your data set X. To classify whether apple or oranges is your task. Okay. So classify the data X into two classification, that is C1 and C2. Yes. How we can say, if W transpose Xi is greater than 0, then Xi belongs to C1. If W transpose Xi less than 0, then Xi belongs to C2. That's how we classify automatically, right? That's how we classify automatically. Fine. Okay. So can you understand what should be the decision boundary here? What should be the decision boundary? What should be the decision boundary? See, if for greater than 0, class 1, less than 0, class 2, then what happens in the middle? So W transpose X equal to 0 is the decision boundary. So I hope this, how to compute decision boundary, you can compute like this. So given a set of weights, given a set of inputs, just compute W transpose X equal to 0. That will give you the decision boundary of that classification problem. So this is the dividing line. This is the dividing line. For 2 dimension, this will be a line. For higher dimension, it will be a hyperplane. So therefore, if you read any books or apply to any perceptron to anywhere, reading any books of ANN, artificial intelligence, you will see the word hyperplane because they will write general terms. But when you consider the lower dimension, that is 2 dimension, it will be a line. Okay. I hope that is clear. Fine. So this is the idea of classification that I told you. Decision boundary, you saw a logical interpretation, how to compute the decision boundary. and how to actually find the decision boundary efficiently using support vectors. Support vectors. The wider the buffer, the better the decision boundary is. So the wider buffers are like support vector machines can find out. Okay. And you can actually find the equation of the decision boundary by setting W transpose X equal to 0. I think you might not have seen this expression elsewhere. Did you see this expression W transpose X equal to 0 somewhere? Yeah, so that's the difference. That's the flavor this course will bring to you. Like, you try to understand whatever you have already learned so far, but you try to add a bit of logic and a bit of reasoning behind this, why it is being considered. Okay. Fine. Some are in my notes. Okay, there is an example in my note where we are considering. Oops. Okay. Maybe how I can show this, I don't know, but okay. So let us consider this example, test data. I want to give you a real example of how you can take a data set from a project, from if you're working on some real world project, and you have to first create a data set out of it. So once you create a data set, how you can apply this classification problem. So suppose you are running your house. Okay. So in your house, how you get water? Tap. But from tap, where it is coming? Huh? Tank. From tank, how it is coming? Huh? Underground. From underground, how it is coming to the tank? But we want to know. Okay. So we are considering the motor. Okay. And how old is your motor? 5-6 years. Who has the oldest motor in their house? Motor doesn't usually gets broken. Okay, but an older motor has higher chances of breaking down. Who has of around 10 years or 15 years? Yes, you can see. So yeah, so the motor is good quality. What is the motor? What is the motor? Huh? Okay, this is our motor. Okay, so you use the motor every time. To use the motor every time, and what you do? Switch on the motor, and suppose one day motor did not work, then you know it is fault. Okay, but how to predict that it is fault? How to predict that it is fault? So therefore we have to run some test. You have to run some test. How you will run some test? Test number 1, motor age. You want to classify maybe whether tomorrow the motor will work or not can be given you. You can get a knowledge of it. How you can get a knowledge of it? You can collect every person, like in Durga's house, what is the motor's age and whether it is working fine or not. How much is the motor age? 3 years, 10 years, 20. Just randomly you have to tell. Anyway, suppose 15.5 years. 15.5 years the motor has been working, and after 15.5 years, what is the output? Worked or not? Working condition. One, suppose fail. Okay, fail. That after 15.5 years, motor stopped working. So failed in work. Similarly, test number 2, when you have 23.75 years, it failed. So similarly, you generate some data. Suppose 8 years, fifth data set, 8 years passed. Pass means it is already working, 8 years. So you can see that the motor with lower age works better as compared to motor with higher age doesn't work better. So we want to classify, we want to know which motors, we want to know a classification of the working motor and the age of the motor. Relation between the age of the motor and the working condition of the motor. So we want to place it. We want to place all this data onto the plane. Okay. So what you will have two clusters. You will have some motors in working condition and some motors in non-working condition according to their age. That you can classify using this decision bound. Okay. So next time, if one of your friend tells that my motor is of this many years working already, so you can place it in any of this, you can plot the point, and if it is very close to the decision boundary, you will know that the motor is about to get broken, because the once it crosses the decision boundary, it will be the faulty one. You understood the idea, right? So I am telling you how real world problems can be classified using this classification technique and can help you determine whether the motor is about to break. Okay. If you can find, suppose this is 16.9, okay, and after 10 days, suppose it crosses the line, then you can expect that the motor is about to break within 1 month. Chances, there are chances. So you can predict like this. Okay, so this is one of the example. Fine. So yeah, you can do a multiple classification test also. Like you can add a temperature to it. You can add a temperature to it. If the motor is very old, it gets hot very soon. Your laptops, for example, the older the laptop is, the older the laptop is, the hotter it will get, isn't it? The older the laptop, much hotter it will get. So therefore, depending on the motor age and temperature, you can also predict. So if you add temperature, it will be a multiple linear regression. Y cap will be a function of x1 and x2. This is x1, this is x2. Similarly, a lot of other parameters into picture. I hope that is clear. Okay. Fine. These are all I wanted to talk. Yeah. Yes. So task of individual neuron may be simple enough, but when you combine the neurons together in form of a network, okay, that is not that simple. Okay, you get the you conduct complex processes like regression, classification, all those things. So another kind of simplest neural network is feed forward neural network. Okay, feed forward neural network. What does it does? What work it does? Anyone? Forward neural network. You might have learned, right? What it does. How many of you know? Hmm. Why it is known as forward? Hmm. Backward. Then why it is called only forward? Yeah. Yes. So feed forward neural network has unidirectional information flow. Okay. Therefore, forward information comes. So from input to output, you have unidirectional flow of information. So feed forward neural network, unidirectional flow of information. That's how he got its name. Unidirectional flow of information from input to output. Okay. And in this kind of neural network, you usually see something known as hidden layers. In this kind of neural network, you will see something known as hidden layers. I think you already come across this already. Hidden layers. What is the work of the hidden layer? So hidden layers are the layers which come across in between both input and output layer. Okay, they come in between input and output layer, and yes, each hidden layer can have their own set of nodes, but they usually come in between input and output layer. And fine. So yeah, uh, I think we can, now is the time. I think we can see some examples. Now you know that what is hidden layer. Okay, let us see. Let us see the Python coding for this. find. Mm. So we want to learn multi-layer perceptron. So far you have seen like how regression can be used for neural network sense. Now the idea is, can we use multi-layer perceptron to solve it? Okay. I'm trying to find where it is. I think I saved it here. Last class I was showing you that error error bar plot, right? Where it is. I think this one. Anyway, I think maybe we can look at it next class. Okay. So how you can use multi-layer perceptron. Okay, I'm not getting it here. Uh, yeah, I think we got. I think we got it. So yeah. So whenever you want to do this machine learning task, you have to import this scikit-learn. So you can see this sklearn here dot matrix. Fine. So what I'm doing here is simple thing. Is I want to add these two sine terms. So I want to add these two terms, that is sine 5x and sine 0.5x. This should come to you as handy because we learned this in the last semester. What happens if you combine sine and cos terms? Addition, Fourier transform and all this. So this is the first term. This is the fast oscillation. This will make the oscillation very fast. And this is slow oscillation. That is, it will oscillate slowly. These two terms we add, so together it will look another like a sine wave kind of thing. Okay. So, and we are adding some noise to it. So this is the fast oscillation. This is the way we are creating the data set. Nothing else. This is the artificial data set. This is the artificial data set we are playing with. The artificial data set. Artificial data set we are playing with. Sine term, sine 5x, sine 0.5x, and then we are adding the randomness to it. Okay. So therefore, you will see something like a sine wave, but it will not exactly be the sine wave, rather the splitting on that curve, like nearby that. Okay. Something like this, something like sine moving kind of points. And we want to find the best regression curve to this nonlinear. Okay. To this, we use MLP, multi-layer perceptron, to do this. So this is how the data set looks. Okay. So you can see using the randomness, it tells you that this point, suppose take this point for example, this point can only oscillate from this to this or this to this due to randomness. It cannot move away from it. Okay. That these vertical bars mean to you. Due to the added randomness, this point, the actual data set can move either to maximum up to this or maximum below up to this. Cannot move away from that. That's how variance we have given. That's how the mean we have given. Okay, fine. So this is the data set, how it looks like. Fine. We want to use the regression. So when you plot the regression line or the regression curve, what it should be the output? Like, can you tell? So the regression output should be in such a way that it should not leave out this line. Got the idea? Like, if your regression curve is this one, this is the data point, then the regression curve should either go like this or like this. It cannot go this. It cannot go this. It can go either way. It cannot go above or below that line. Okay, it can come anywhere in between the two error lines. Cannot curve anywhere away from that line. That's the idea. Okay. So if it happens, it's a good regression model. If it doesn't, it's not a good regression. Okay, that's the idea. So this is known as an ANN model for regression is known as MLPRegressor. Stands for multi-layer perceptron regression. Okay, so we will use the above for this noisy data because we have added our own artificial random noise to it. So it's a noisy data. So whether this multi-layer perceptron works for the noisy data, that's the question. That's the question. So from sklearn.neural network, you are importing this regression. Fine. Then we will see. So this creates, if you write this line, this creates an instance of MLPRegressor class from scikit-learn, which is a multi-layer perceptron model. This model is configured with 3 hidden layers. Okay, as you know, hidden layers lie in between the input and output layers. 3 hidden layers I have taken. You can take 5, you can take 6, you can take 7. Okay, you can take 8, however you like. Okay. And each hidden layer will consist of neurons. How many each hidden layer consists of? But also it's with up to you, up to your choice. Okay. Here we have taken 200 neurons. So what is the output? The idea is simple. The idea is simple. Like, I want a better pen. Can you bring one black and one red pen? Okay, fine. Other parameters of that include the maximum number of iterations, take the number of epochs, the forward and backward propagation you want to make. Solver algorithm used by MLPRegressor is something known as LBFGS. Okay, it is a quasi-Newton optimization algorithm which we have not covered in class. So I wanted to cover these kind of algorithm which you see in deep learning or machine learning randomly, but is usually not covered. Okay, but in anyway, like we did not get enough time, but maybe some next class we can do. Next class we can try. So there is something known as regularization parameter alpha. The activation function is taken to be tan h. I suggest you take this code and use ReLU activation function, or use softmax or any other activation function. And fixed random state for reproducibility. Fine. Fixed random state. This is important. Fixed random state for reproducibility. Since it is random, since you are using randomized to noisy data, okay, if you run it for another instance, tomorrow if I want to learn, or after again second iteration if you want to do it, the dataset will change. The dataset will change, right? Because the dataset is random. It can change. How you can fix that random state for all the iterations? How you can do that? Yeah. How many you know about seed? Not that plant seed. The idea originates from that plant only. No. That seed will give you that plant only. So therefore, how many of you know about seed in statistics? Seeding, seed in statistics. Very important. I suggest when you go home after this class, read about seed statistics. Very important concept. Very important concept. Okay. So we'll see this in the code. We'll see this in the code. So the idea is the same. So you can see we are fixing the random state. So okay. Random state equal to 8. Random state equal to 8 is given. That means seed. Suppose you do one iteration run of your code, rand of 8. Okay. And this you apply seed 1. This you apply seed 1. So whenever you want to access this set of random states, that is suppose 8, 3, 2, 5, 6, 7, whatever you are getting the random numbers, okay, 8 set of random numbers, if you apply seed 1 to it, so whenever you apply seed 1, you will get all this data set again. That's the seed. Okay. Whatever rand you 8 you do, seed if you apply is 1, it will always give you this set again. Usually randomness doesn't give you the same output, right? But if you apply the seed 1, it will give you the same output. So that's the way of saying this. Fixed random state. Fixed random state. Okay. Understood. Random is random. Why you fix? Fixed random state. That you do by seeding. That's the actual performance of seed. Okay. Fine. Okay. So fit the MLP regression model to the training dataset x, y using the fit method. The x variable is reshaped to have a single feature. Fine, it's not required. Yeah, okay. Using xfit, you are doing it. MLP regression. You can see MLP regression, what kind of input it is taking. It is taking the hidden layer size. The hidden layer size is 200, 200, 200. What does it mean? It has 3 hidden layers and each hidden layer has 200 neurons with it. And maximum iteration you are performing is 2000 iterations. What kind of optimization algorithm you want to use in that MLP regression is also up to you. You can use LB, FGS. I suggest go home and try to find what other solvers are there. LB, FGS, I have written it down, but you can use other algorithms also. But what kind of other algorithms are there? You need to know. Solver. Try to go into the manual. Read the manual of MLP regression. Go home, read the manual, optimization manual of MLP regression in Python. Okay. There it will tell you all the input quantity it is taking. Okay. What is the solver? Next class you will tell me what are the different kinds of solver. Okay. What are the different kinds of solver it has? And what does it mean for random state equal to 8? Who will say this in next class? Chaco. Okay. Chaco will tell us, Mr. Chaco will tell us, what does it mean to have random state equal to 8? Class coordinator, you should remember. Class coordinator, they should tell. Okay. So xfit is np.dot linspace. We are dividing the text into 0 to 10. Y true model xfit, comma 0. Fine. And then you do mlp.fit. mlp.fit, give the data sets, that's done. Nothing else. Give the data set into mlp.fit, it will do all this for you. That means it will carry out the regression process with this particular architecture. That's the idea. Given the set of X and Y data, MLP regressor will use its own neural network algorithm with this architecture which you have defined, with the particular optimization function which you have defined, okay, and with the number of iteration which you have defined. Based on that, it will do the regression, okay. And this is how it looks like. Yes, you can see the red one is the predicted one and the gray one is the actual data set. The gray one is the actual data set, like which is you can plot actual data set with added randomness, okay, with a particular seeding value. And the red is the regression data set, regression line, sorry, regression curve, okay, for coming from MLP regression. Fine. So you can see that only one of them has moved out of that zone. Can you see all of them have remained in the zone, but only one of them have gone out of that particular data zone. Others are oscillating in between that variance only, maximum and minimum variance. Okay, other data sets are okay. Other data sets, you can see they're oscillating in maximum to minimum variance, but only one data set has gone out of that. This is a bad prediction. This is a bad prediction. It's bad. So this part is a bad prediction. Other parts are good. Yeah, this one is also there. Somehow nearby. So you can see how MLP can do the regression task for you. Okay. You can see that the fitting of the data is not that bad. For the above model, we have used 3 hidden layers, and in each layer we have used 200 neurons. And LBFGS algorithm has been used. This is an optimizing algorithm coming under quasi-Newton family of methods. Okay, you learned Newton. Then I told that there are some limitations in Newton's method which can be solved using quasi-Newton methods. Yes, and this is one part of this. You can see that MLPRegressor did not use Newton's method rather than a quasi-Newton method, which is better than the Newton's method. Okay, did not cover quasi-Newton, but maybe if time permits, we can. Fine. So this is so far all the things I wanted to teach in this lecture. Next lecture onwards, we will start with PDEs and ODEs. Okay, partial differential equations and ordinary differential equation. Those will be the two remaining models of this lecture. If we finished it well within time, I can cover these parts, that is LBFGS. So can you note it down? LBFGS algorithm, quasi-Newton methods, because these are actually being used in your machine learning algorithms, and it is most important for you to learn it. Now it is very new to you, right? LBFGS is very new to you. What is that? You just know the word LBFGS. Okay. What is after that, you don't know. Okay. That's the idea. That's the idea. Anyway, this is so far we have covered. Any questions you can ask.